In this video, we're going to look at a very classic group theory result known as the Sylow theorems. And in this video, we're just going to prove the theorems, but in an upcoming video, or maybe a follow-up if you will, we'll look at lots of examples of applications of these theorems. But we need some definitions first, as well as to recall some of the things that we've perhaps proved before. So let's say that P is a prime, and the order of a group G is m times p to the r, where p does not divide m. So in other words, this is like factoring the largest power of p out of the size of the group. Then, if we've got a subgroup capital P of our group G, it's called a Sylow P subgroup if the order of P is equal to P to the R. So it achieves this largest power of the prime P. And well, what we'll show first is that every group has a Sylow C subgroup, or a Sylow P subgroup, I should say. But we're going to need some tools here. In particular, we're going to need the class equation. So let's recall that. So let's suppose that x1 to xk are representatives for conjugacy classes of a group G. So G is acting on itself via conjugation, but these are representatives where those classes have more than one element. Let's recall that if the class has exactly one element, then the element is inside the center, and we want to look at that on its own. So in this case, we can decompose the size of the group as the size of the center plus all of these indexes. So this is the index of the centralizer of x1 in G added all the way up to the centralizer of xk in G. And let's just recall the definition of the centralizer. So the centralizer of xi is every element of G that commutes with xi. So much earlier, we probably proved that this was in fact a subgroup. And then let's recall that the center, which we call ZG, is just everything that commutes with everything else. Okay, so we're going to start off with a proof of the first Sylow theorem. And what it says is, well, like I said down here, every group has a Sylow P subgroup. So in other words, if G is a finite group and P is a prime such that P to the R divides the order of G, then G has a subgroup of order P to the R. Now, observe that this is a bit more general than our result down here. Our result down here is that we've got a subgroup of order, maybe the largest possible power of that prime dividing the group. And this just says any power of the prime. So that's pretty cool. Okay. Nice. So how are we going to prove this? Well, the strategy is to use induction on the size of G. Okay, so if we're using induction, we of course need some sort of base case. And in this case, the base case will be, well, what happens if the size of G is just P? So in other words, the order of G is P. And I would say in this case, we're completely done because, well, check it out. Every power of P that divides the order of this group has a subgroup. It just turns out that in that case, it's just the whole group. So it's not super interesting, if you will, in this case. Okay, so now let's move to the induction step, which of course starts with an induction hypothesis. So this is going to be strong induction, if you will. So let's suppose that the statement holds for all groups of order m where P divides m. I didn't write that, but that's understood. With m being between P and n. So notice that the role of m here is different than the role of m over here. So just make sure to notice that. Okay, so now that we've set up our induction hypothesis, let's consider the class equation. So I'll just rewrite that as it's written over here. Okay, so there we've got the class equation. And now we're going to break this into two cases. And those cases have to do with the divisibility of these indexes with respect to P. So let's start with our first case, and that would be P does not divide this index of the centralizer for xi in G. And this is going to be for some I between 1 and k. Okay, so in other words, we've got p does not divide this index. But let's recall that p to the r divides the order of g, but then we can write the order of g as this index, so the index of the centralizer of xi in g times the order of this centralizer subgroup. So p to the r divides this product. We know that p to the r does not divide this term, which means p to the r has to divide that term. We know that that kind of thing works because we're working with a power of a prime here. So in other words, we've got p to the r divides the order of this centralizer subgroup. But in this case, we're totally done because by induction hypothesis, our centralizer subgroup has a subgroup itself of order p to the r. That's because the order of the centralizer subgroup is smaller than the order of the whole group. Okay, so now let's move on to our other case. And of course, if our first case is that p does not divide one of these indexes, then that means that our second case, the complement case, if you will be p divides every one of these indices. But now observe that if p divides everything in this sum right here, well then it divides the whole sum. But then if it divides the whole sum, and it divides this side of the equation over here, this g, that tells us that p most definitely divides the order of the center, because it divides their difference, which is the order of the center. But then by a structure theorem for abelian groups, which we probably would have looked at before this point, we know that that means that the center has an element of order g, because the center itself is an abelian group. So let's write that down. So there exists a little g inside of the center of g such that the order of little g is equal to p. Again, that's by a structure theorem for abelian groups. But now what we want to look at is the cyclic subgroup generated by this g, which is a normal subgroup of the entire group. Well, how do we know it's a normal subgroup of the entire group? Because it is in the center. Every power of little g is in the center. But if every power of little g is in the center, it clearly generates a normal subgroup. Okay, great. But since it generates a normal subgroup, the natural thing here is to look at the quotient group. So let's do that. So since p to the r divides the order of g, we know that p to the r minus 1 divides the order of g mod little g. And that's because, well, how many elements are in this cyclic subgroup? Well, they're kind of obviously p elements because it's generated by an element of order p. But then p to the r divides this, we're dividing out one of the p's, so p to the r minus 1 divides that quotient group. But now we'll apply the induction hypothesis. So the induction hypothesis implies that there exists a subgroup H of our quotient. So that would be G mod, the cyclic subgroup generated by little g, of order P to the R minus 1. Again, that's by our induction hypothesis. Okay, nice. And now we're going to do a nice little trick to finish this thing off. So let's consider the following maybe obvious projection map. I'll call it P. And it goes from G down to the quotient group G mod, that cyclic subgroup. And what does it do? Well, it takes an element X from the group and it sends it to the coset with representative X. So we would maybe write it like that. But now, much earlier, we proved that the pre-image of a subgroup was in fact a subgroup. So let's set K equal to the pre-image under this map of H. Okay, nice. But then H had order P minus 1, but since this map maps to a quotient where the quote-unquote denominator has order P, that means that this K, which is the pullback, if you will, of this group of order p to the r minus 1, clearly has order p to the r. So here we've got the order of K is p to the r. But that's where we wanted to end up. There is, I guess, one more way to do this. You could use the so-called correspondence theorem for subgroups of quotient groups if you'd like to. Maybe look up that if you want. Okay, so now let's move on. All right, so of course I numbered my first Sylow theorem over here, so you might guess that we've got a couple more coming in. In fact, there are 3 Sylow theorems, and we're going to need a couple of lemmas to prove the second 2. So let's look at our first little result. So let's let P be a Sylow P subgroup of G, and X an element of G where the order of X is a power of the little prime P. Then if X inverse PX is equal to P, in other words, if the conjugate of our Sylow P subgroup by this element X is just the Sylow P subgroup, then X must be an element of the Sylow P subgroup. Okay, great. Now let's get started. So since we know X inverse PX equals P, then we know that X is in the so-called normalizer of P. So I'll write this as NGP. It's the normalizer of P in G. So you can define the normalizer for any set. This is the normalizer of our Sylow P subgroup. So what is the normalizer? So this is going to be all little g in G such that G inverse PG is equal to P. Now let's note the following, and I think this is pretty clear that P is a normal subgroup of the normalizer. So, you know, the normalizer is aptly named. In fact, this normalizer is the smallest subgroup of the entire group that P is a normal subgroup of, if you will. Okay, nice. And now what we want to do is consider a certain subgroup of the quotient, because anytime you start talking about a normal subgroup, you probably want to start talking about the quotient group. So let's consider the normal subgroup generated by the coset XP. So, sorry, the cyclic subgroup generated by the coset XP. So this is going to be a subgroup of NGP mod P, that quotient. Great. Now we're going to apply this correspondence theorem, which is something that we study around the time that we're looking at the isomorphism theorems. So by the correspondence theorem, what do we know? Well, we know that there exists an H, which is a subgroup of that normalizer, with this cyclic subgroup XP is equal to H mod P. So again, that's by this correspondence theorem. Anytime you have a subgroup of a quotient group, you can write that subgroup of a quotient group as a quotient itself, which is what we're doing right here. Okay, so now we're ready for our final, calculation, if you will. So let's look at the size of H. So let's observe that the size of H is going to be equal to the size of our Sylow P subgroup times the size of this, this cyclic group XP. Okay, great. But now, well, what do we know about the order of this? The order of this is exactly P to the R. We know that because it's a Sylow P subgroup. But then the order of little x is P to the K. That means that the order of this is also P to some number. It probably doesn't keep the same power of P it has, but it still has power of P. And that's because the order of an element under the quotient map must divide the order of its original element. And this can be actually generalized a little bit, or maybe is a special case, if you will, of the order of an element in the image of a homomorphism must divide, I should say, the order of the original element, which is something you probably saw before. Okay, so anyway, let's look at what we've got here. We've got this thing right here is order of a prime. This is the order of a prime. That means that the size of h is also an order of a prime. But notice that the order of the prime here is p to the r or larger. So that means the order of h is equal to p to the, I'll maybe put s here, with s bigger than or equal to r. But let's look at this. We know that the largest possible power of a prime subgroup is the Sylow P subgroup, just by the definition of Sylow P subgroup. So that means that this s must be equal to r. In other words, the size of h must be p to the r. But now we can fill this equation in over here and say that this is also p to the r, but that means that this has order 1. But that means that this cyclic subgroup here is the trivial subgroup, but that occurs if and only if we have x is an element of p. But look, that's where we wanted to end up. So we've proven this lemma. Okay, so I think we've got one more lemma before Sylow number 2. Okay, so this is a little bit of a technical lemma, but we will need it. So let's suppose that h and k are subgroups of G. Then we have the following equality. So the number of h conjugacy classes of k, which in symbols is just this right here, is the same thing as the index of the normalizer of k intersected with h in h. But observe, that's the same thing as the number of right h cosets of this normalizer of k intersect h. So how do you check that these two things are the same number? Well, we're going to find a bijection between them. So let's consider this map that takes conjugacy classes to cosets. And here's what it's going to do. So it's going to take the conjugacy class h inverse kh, and it's going to send it to kind of the obvious coset. So that's going to be ngk intersected with h with representative little h. Okay, so I'm going to just say that this is pretty clearly surjective. How do we know it's clearly surjective? Well, notice that a right coset is going to have this form. And so we just take its representative over here, and we form the conjugacy class out of its representative, and then that's going to be sent to the appropriate coset. You might worry that conjugacy classes have representatives, so they might have different names, if you will. So you might want to check that this is well defined. I'll leave that to you. We'll just focus on showing that this is injective, which is actually not so bad and allows us to review some rules about when cosets are the same. So let's suppose that we have f of h1 inverse k h1 is equal to f of h2 inverse k h2. So those two conjugacy classes. But let's observe by the definition of our function, that means the corresponding cosets are the same. So let's get those cosets written on the board. So we've got this normalizer in G of k intersected with h, h2 coset. Okay, nice. But now we know something about coset equality from when we first learned about cosets and normal subgroups and the like. And two right cosets are the same if and only if you take their representatives and combine them like this. So h2 inverse h1, you get something inside of the subgroup. In this case, the subgroup is this pretty kind of gnarly thing, which is this normalizer intersected with h. But now these being in the normalizer of k means that if we conjugate k with this element, we end up back with k. So in other words, if we take h2, h1 inverse k, and then it would be h1, h2 inverse, we get back to k. So that's just conjugating k with this element, keeping in mind that being inside of the normalizer means that we get this equation. And now we're essentially home free. We'll left multiply by h2 inverse and right multiply by h2. So that's going to clear everything on the left-hand side of the equation and give us h2 inverse k h1 on the right-hand side of the equation. Sorry, that should be h2. But check it out. That means that the two inputs that gave us the same output really had to be the same. But that's exactly what we need to show that this thing is injective. Okay, so now we're ready for the second Sylow theorem. Okay, so put very shortly, the second Sylow theorem says that all Sylow P subgroups are conjugate. But what does that really mean? Let's suppose that P1 and P2 are two Sylow P subgroups of our group G. Then there exists a little g in G such that G inverse P1G is equal to P2. That means that P1 and P2 are conjugate. But since we started with two arbitrary Sylow P subgroups, that means that, yes, all Sylow P subgroups are conjugate. Okay, so let's get going with the proof. So let's say our order of G is equal to m times p to the r, where p does not divide m. And then let's suppose that P is a subgroup of G with the order of P is equal to P to the R. In other words, P is one of our Sylow P subgroups. And now what I want to do is set this set that I'll call S equal to all conjugates of P. So I could write that as G inverse PG as G runs over all group elements. So that's all conjugate subgroups of P. So a priori, we don't know that all of the Sylow P subgroups are in this set, but they in fact will be. That's what we're proving here. But now I'd like to write these out, if you will. So that's going to be equal to P sub 1, P sub 2, all the way up to what I'll call P sub k. So that means we're kind of assuming there are k such Sylow P subgroups. And let's say that this first one is the one that we started with P, just for the sake of argument. Okay, nice. And now let's observe that a previous lemma, one of the two lemmas that we just proved, shows that the order of S, which is equal to k, by the way that we have enumerated it, is equal to the index of G inside of, or sorry, the index of the normalizer of P inside of G. Okay, cool. So now let's also note that P as in the Sylow P subgroup, is a subgroup of NGP. It's the subgroup of a normalizer. So if you take the normalizers of a subgroup, the kind of earlier subgroup is always going to be a subgroup of what? Of the normalizer. Okay, cool. But then P to the R divides this group P. But then since it's a subgroup of this normalizer, that means that P to the R also divides the normalizer, so NGP, just by Lagrange's theorem. Okay, then also, or maybe I used also, so maybe and we have the following numerical equation. So we have m times p to the r, that's the order of our group, is going to be equal to the size of the normalizer of P in G times the index. So here we have the index of that normalizer in G. But that's by Lagrange's theorem, just another way of writing down Lagrange's theorem. But we said that that was equal to K, the number of different conjugacy classes we had, or sorry, the number of different conjugate subgroups we had. So we could rewrite this as NGP, the order of NGP times K. Now check it out. We've got P to the R over here. We know P to the R divides this order of this subgroup, but that means that P cannot divide K because we've used up all possible powers of that prime. Okay, so now that we've got P does not divide K, so in other words, P does not divide this thing right here, which is the number of conjugates of our original Sylow P subgroup. So now what we want to do is suppose that Q is another one of these subgroups. So in other words, another Sylow P subgroup. And now we want to consider the following strange collection. I'll call it S sub I. And S sub I is going to be equal to G inverse, little g inverse, and then P sub I, and then little g, as little g runs through all of the elements of Q. So we're just taking, let's see, each of these things right here, and we're conjugating them by elements from Q. And let's notice that if we take all of these sets and throw away the ones that are repeated, and then collect them together, this forms a partition of S. So I think that's, pretty clear, if you will. And then let's also note the following, and now we're about to use that technical lemma. And that is that the size of Si is equal to the index of this normalizer of Pi intersected with Q inside of Q. And we know that P to the R is equal to the size of Q. But then the size of Q can be written as a product of two things built out of this. So in other words, the index times the size of the subgroup. So this is just the subgroup over here. It kind of got smushed, but I think that's pretty clear. But let's see, we've got two things over here whose product is a power of P. That means that each of them must be a power of P. So in other words, for all I, we have this index, Q indexed, the normalizer subgroup of Pi intersected with Q in Q is a power of P. But we also know that if we add all these together, we get K. Because notice that Si is a partition of this set over here. So just in other words, if we add all of these together, we get K, but each of these are a power of a prime. But then our prime does not divide K. So that means one of them must be the 0th power of that prime. But the 0th power of that prime means that one of them only has one element. Okay, so to reiterate, one of these SIs has one element. But you know that the original P sub j, if you will, is an element of this. So that means that has to be the only element. So that means that for all little g in Q, we have G inverse Pj, G is equal to Pj. But why is that done now? Well, let's notice that G has order power of a prime. But we know that if we do this conjugation with an element of an order of a prime, a power of a prime, and we end up back in that Sylow P subgroup, that means that element has to be in that subgroup. That's again by one of our previous lemmas. So that means that our G is inside of Pj. But that means that this Q is a subgroup of Pj. But then they're subgroups of the same size, which means that Q is one of the Pj's. But if Q is one of the Pj's, well then we took our arbitrary Sylow P subgroup and showed that it was one of the conjugates that we wanted it to be. And that's the end of this theorem. Okay, so now we've got one more Sylow theorem. So our last Sylow theorem is a bit of a counting theorem. So let's let NP be the number of Sylow P subgroups. Then NP is congruent to 1 mod P, and NP divides the order of the group. So if you've got certain groups of certain orders, I should say, this really restricts the possibilities for NP, as we'll see when we look at applications. Okay, so let's see how this proof goes. So let's let capital P be a Sylow P subgroup, and it acts on what we'll call S, which is going to be equal to P1, which we'll call P, and then P2 all the way up to Pk by conjugation. And what is this S? Well, I'll just say it in words, I won't write it down. S is the set of all Sylow P subgroups. So in our notation, this K, because it's the counting the size of S, is equal to N sub P. And now let's recall the class equation, not in terms of groups, but just before we had it in terms of groups, which was in terms of groups acting on sets. And that said the following. The size of our set S, which is equal to K, so nothing is done there, is equal to the size of S sub G. Recall that's everything fixed by the elements of the group, but I should say the group here is P, so that should be S sub P, the Sylow P subgroup. And then plus the size of the orbits. So I've got to strangely index these, so this is going to be the orbit of P sub I1 plus all the way up to the orbit of p sub I, let's maybe say m here. Great. Where those p sub I1 up to p sub I m's are from this list right here. They're like representatives for each orbit. And now let's recall what this S sub capital P is, just so we know what's going on here. So this is going to be equal to all P sub I, where G inverse P sub I G is equal to P sub I. And this is going to be for all little g inside of our capital P. That's because our Sylow P subgroup is acting on this set via conjugation. These are the fixed points of that action, if you will. But then we know that the following is true, and that is there's only one subgroup that's fixed by the conjugation action by P, and that is P itself. And we don't know that from the statement of a result, but we know that by the proof of the second Sylow theorem. Remember that we got that one conjugacy class of size 1 inside of the proof of that theorem. But then by the class equation, we know that the size of all of these orbits, so I'll just put a box down there for meaning all of the orbits, is a power of a prime. So I'll just put P to something for a power of a prime. And it's a non-zero power of a prime because the only thing with the zero power of that prime will be this fixed one down here. But then if we put that all into this class equation, observe that we have K is equal to 1 plus P times a bunch of stuff. That's because all of these are powers of primes, so if you add them together, you get a multiple of the prime. But then if K is equal to 1 plus P times something, that's pretty clearly congruent to 1 mod P as needed. That's this first result. Okay, so now let's get on to that second result. So now let's let just G itself act on S by conjugation again. But then we know by Sylow number 2 that all Sylow P subgroups are conjugate. So what that tells us is that the size of S, which is again K, is equal to the orbit of P, the size of the orbit of P, because everything is just a single orbit here. But then again, by stuff we did when we were learning about the class equation, that's the same thing as the index of the normalizer of P in G. And then by our previous lemma, this index divides the order of the group, which means our K, which happens to be equal to that index, also divides the order of the group. And there we have it. We've got this theorem is proved. Okay, so now I'm going to leave you with some exercises. Okay, just a few exercises because more exercises will come after we do a big application video. So the first one is to find all of the orders of Sylow P subgroups if the size of G comes from this set. So it's either 18, 24, 30, 54, or 72. And then next, let's find all Sylow 3 subgroups of S4. And notice that they are guaranteed to be conjugate. So if you want to show precisely how they are conjugate, that would be good as well. And that's a good place to stop.